Hi folks, this is Sophia, and this is my Lab 5 report. Okay, so in Lab 5 we explored Faraday's law and the concept of induced magnetic fields and induced electric currents by dropping a magnet through an aluminum foil tube. So while the magnet was falling, the magnetic flux through the aluminum tube was changing. And so this changing magnetic flux induced an EMF in the aluminum foil and also induced a current. And this current induced a magnetic field in the direction that opposed the change in the magnetic flux from the magnet. So yeah, so we basically used Faraday's law and Lenz's law. Okay, so the first thing we did was we had an aluminum tube and we physically dropped a magnet into it. So the aluminum tube was, the aluminum itself was 0.015 meters wide, and the length of the tube was like 0.45 meters. Okay, so we taped this tube to the wall and dropped a magnet through it, and from rest, and then we recorded the duration that the magnet was falling through the tube. And the idea was that while the magnet is falling through the tube, the induced magnetic field in the aluminum would apply a force on the magnet, in the upwards direction, because the induced magnetic field is also acting in the upward direction to kind of counteract the increasing downward flux from the magnet. And that should slow down the magnet compared to if it was just falling in free fall. And next, we modeled the same situation in GlowScript. So we had the tube modeled as a collection of rings, tiny rings dy, and so the code calculated the magnetic flux through each of these rings as the magnet changed position. So, change in flux equals area of the ring times the change in the magnetic field, and then we use this long formula for the magnetic field from Lab 3. And so the magnetic field is dependent on the distance between the magnet and the ring of interest. So of course it changes as the magnet changes, or as the magnet changes position. So we basically, for each position of the magnet, we summed up the magnetic field and flux for all the rings, and that's how we got the overall results. Okay, and so what I got was, experimentally, I measured that my magnet took 0.2 seconds to fall through the tube, and GlowScript predicted 0.303 seconds. So this is pretty short, and I'm pretty sure this is partly because my magnet's magnetic moment was pretty weak, 0.27. Yeah. And as you can see, the velocity versus time graph didn't turn out as it should. It was linear, so the velocity linearly decreased as time went by, whereas in my classmates' graphs, I saw that the velocity, decreased pretty steeply and then kind of increased. So yeah, it had like an exponential steep decrease. And then it briefly increased as the magnet exited the tube, and then kept at a steady value as the magnet reached terminal velocity. And I'm guessing my decrease was a lot smaller, also because, the magnetic moment was weak. Okay, and some potential things that could explain the discrepancy between the experimental and the computational time for the magnet to fall was air resistance, or maybe the magnet didn't fall in a straight line or hit the tube, or maybe my magnetic moment was slightly off. Okay, and so finally, for the conceptual questions, if the resistance was 0 in the aluminum foil, then it would be a superconductor, and as the magnetic flux was changing while the magnet was falling, the induced current would be in the aluminum would be very large, and it would create a very large induced magnetic field. And this magnetic field would apply a force on the magnet that would be strong enough to stop the magnet. So the gravitational force would be equal to the magnetic force, and the magnet would just sit there and hover. And then if we cut some holes into the foil, then we would no longer have a closed loop, and so we wouldn't have any induced current and the whole experiment wouldn't work. Alright, well, thank you for watching. Have a great day.